And so let's start off with a basic question, and that is, what is heat? Normally when people talk about heat, they think about it in sort of a general, sort of almost emotional sense, is that it's warmth and things like that. But that's really not a very technical scientific definition. And overall, the scientific definition of heat is that what heat is if you think about molecules and atoms, is that these molecules and atoms tend to move around just by their nature, is that they have either some lateral movement, sort of almost like a jiggling type movement. They do have some rotational movement as well, but mostly we're interested in that sort of back and forth jiggling type motion, the same way that if you took like a piece of Jell-O and put it on your plate and shook your plate, you'd see it sort of jiggling back and forth. And so that type of motion, so this back and forth motion, is basically what heat is. It's the motion of molecules and atoms back and forth as they run into other atoms and other molecules, and they bounce back and forth. And so this motion that's in here is basically what heat is. In a technical sense, the technical term for this is called kinetic energy. Kinetic is motion. You talk about, say, kinesthetics. You're talking about doing things that are moving, as opposed to static exercises where you're just holding something. So kinetic energy, and so if we're looking at heat, heat is basically, we said, is kinetic energy. So kinetic energy. So heat is basically just kinetic energy in of itself. The total amount of kinetic energy in something is the heat it has. Now, how does that compare with temperature? Temperature is something that is similarly related. And so temperature is also a measurement of kinetic energy, but the difference is that temperature is a measure of the average kinetic energy in something. And so if heat is the total kinetic energy, temperature is the average kinetic energy. And so if I talk about something having a certain temperature, then I'm basically saying that on average, each molecule or each atom in that substance has a certain amount of kinetic energy. If I talk about the heat in some substance, I'm saying that all of the atoms combined have a kinetic energy of a certain amount. And so temperature, we know actually a fair amount about this because we're used to measuring things in temperature. In this class, we'll be using the Celsius scale, at least to start with. For this unit, we'll certainly be using the Celsius scale. We'll get to another scale, the Kelvin scale, later on in the year. But for right now, is that our temperature is measured in degrees Celsius for this unit here. Heat, though, has another unit, one that you're probably not familiar with in this sense, but used to running into another sense, which is the unit of heat is the calorie. And a calorie is simply defined as this. It's the amount of energy needed to raise the temperature of 1 gram of liquid water by 1 degree Celsius. So if you added 1 calorie of heat to 1 gram of water, then it's going to go up by 1 degree Celsius in temperature. And so that's our calorie here. Now, we do need to be a little bit careful because the one place you have heard of calories before are in food. And so when you talk about food, you may say, okay, that this, you buy like a 100-calorie pack of like Oreo cookies and they only have 100 calories. But the calorie that's used there is not the same as the calorie that we just defined. The calories that are in food are right here. They are noted by the fact that they have a capital C out front. They are technically, whoops, I don't know what I just did there. I have no clue what that menu is. I've never seen that before. So basically, is that calories, so as in food, is technically what we actually call a kilocalorie. That is, that it is a kilogram calorie. As before, on our previous definition of calorie, it says the amount of energy needed to raise the temperature of 1 gram of liquid water by 1 degree Celsius. For food, the calories that they measure things in are not the amount of energy needed to raise 1 gram of liquid water. It's the amount of energy needed to raise 1 kilogram of liquid water. And as a result, the type of calories in food are 1,000 times as large as the lowercase c calories that we're going to look at in this class. And so food calories are kilogram calories, the amount of energy needed to raise 1 kilogram of liquid water by 1 degree Celsius, versus the calories we'll use in this class, which are the amount needed to raise 1 gram of calorie, or 1 gram of water by 1 degree Celsius. So we will use the smaller scale. Just as one quick sort of note, because you will see this in other places sometimes, another unit of heat that can be measured in is the joule. The joule is more used in physics, and but 1 calorie is equal to 4.184 joules of energy. And so that's just something just to be aware of if you go on in your science career to see some other things. So let's take a look at a little more here. specific heat. This is going to be our first topic sort of within this idea of a calorie here. We said that we defined a calorie to be basically the amount of energy needed to raise 1 gram of water by 1 degree Celsius. Now, what if we don't have liquid water? What if we have liquid something else? What if we have solid water or a gas instead? What we do for that is we're going to have to look at something called the specific heat. And the specific heat is defined as the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. So not just water, any substance. So technically specific heat is quite simply saying this, is that, if I have 1 gram of iron and I raise 1 gram of iron by 1 degree Celsius, however much heat it takes to do that is the specific heat, or sometimes also called the specific heat capacity of iron. Now, here's the overall equation that we have for this. So, Q equals Cm delta T. And so here are the parts that we have for this. The first part here is Q. Q is quite simply just the heat energy. So it's the energy or the heat. And so that right there is Q. So Q is the energy or the heat. The unit of Q is going to be, as we talked before, the unit of heat is calories. Okay, so Q is energy, and it's measured in calories, or it's also measured as heat here. I know Q does not look anything like heat or energy. It comes from a German word, and so the Germans got to name the variable. So that's our first bit here. So Q is energy. Now, on the other hand, our next variable that we run into here is C. C is the specific heat constant. And so we sort of see some of them down here. I sort of list some specific heat constants for water down at the bottom here. But the specific heat constant, just in general terminology, is usually called the specific heat. So if it ever says, what is the specific heat of this substance, they're talking about this C right here. They're talking about the specific heat constant. For the specific heat constants, they differ depending on what substance you have. So water has a different specific heat constant or different specific heat than iron does, or alcohol does, or lead does. Typically, the specific heat is really a measurement of how much energy that substance will hold, sort of how resistant it is to temperature raising, which is, so if I give it a lot of energy and the temperature doesn't go up very, very much, that means it's storing a whole lot of heat there. It's storing a whole lot of energy, and that would mean it has a very high specific heat. Something on the other hand, like I say, a piece of metal, if you were to take a metal fork and just put it onto the burner on your stove, and while the stove was on, it wouldn't take a whole lot of time for that fork to get extremely hot. Its temperature rises very, very quickly with only a small amount of heat, and therefore it would have a very, very low specific heat. So specific heat and specific heat constants change based on what substance you have, and they also change depending on what phase that substance is in. Take water. So we've got the numbers for water down at the bottom here, is that for solid, water has a specific heat of 0.53 calories per gram degree Celsius. If it's a liquid, it's just 1 calorie per gram degree Celsius, and that's where our definition of calorie came from, is that 1 right there. But if it's solid, it's 0.48 calories per gram per degree Celsius. So effectively what we can sort of see from this is that if I give, say, liquid water, if I add 2 calories to liquid water, then it means basically the temperature is going to raise by 2 degrees Celsius. On the other hand, if I were to take solid water, though, I take ice. If I were to raise ice by 2 degrees Celsius, it wouldn't take 2 calories to do that. It would only take 1.06, 0.53 times 2. So it takes less heat to heat up, to change the temperature of solid water, or of, that says solid down here. That should actually be gas down there. So change that to gas. So the gas form of water is 0.48. So completely ignore the fact that says solid. I've been misreading that the whole time here. And I brought up that little screen again, which I don't know what that is. So basically this is what we have so far here, is that different specific heat constants differ depending on what substance you have and what phase that substance is in. So that's what C is. So C is our specific heat right here. M is quite simple. M is just the mass. It's going to be measured here in the units we're going to have here are going to be in grams. And so that's what our mass is right there. And our last one is one that that it looks like it's two different things. It's delta T, but delta T is actually just one variable. The delta, which is this first letter right here, it looks like a triangle. It's actually the capital Greek letter delta. It means change. Anytime you see it in math or science, it's always going to mean change. And so this is a change in T or a change in temperature. So it's going to be the change in temperature. And the unit that this is going to be in is, as we talked about before with temperature, is going to be in degrees Celsius. And so these are the four parts of your specific heat calculation, is that Q equals Cm delta T, where Q is energy measured in calories or heat measured in calories. C is the specific heat constant. M is the mass in grams, and delta T is the change in temperature in degrees Celsius. So let's take a look at going a little farther with this. And next thing we'll talk about is latent heat. The latent heat of a substance is similar to the specific heat, but instead of being involved with, if you give it heat, it's going to cause the temperature to change. A latent heat applies whenever a substance is changing phase. So if you have ice that's at negative 10 degrees Celsius, that's below the freezing point, you add heat to it, is that as you add heat, that temperature is going to go up, because it's going to make those molecules move faster and faster. But eventually it's going to get up to 0 degrees Celsius. 0 degrees Celsius is the melting point of ice. What's going to happen at that point is that the bonds, which basically the intermolecular forces, the intermolecular bonds, which hold the water molecules in a solid, that make them a crystalline solid form as in the terms of ice, is that those can only basically bend so far until they break. And whenever you've heated that ice up to 0 degrees Celsius, that is as far as those bonds can bend. It's as fast as the molecules can move without breaking those bonds. And so what happens once it reaches 0 is that any new energy you add is not going to go into heating the ice up. It's instead going to go to breaking those bonds that are between ice molecules, between the different water molecules in there. And so as a result, you'll add energy to the system, but as you add energy, it doesn't affect what the temperature is. All it does is it melts the ice. And so you've probably seen this before. You know, you put ice in your drink, and that makes your drink cool off. But then basically the drink doesn't keep cooling on indefinitely. It's not like your drink gets colder and colder and colder. It gets cold to a certain point. And then it stays at that temperature while the ice melts. Eventually, when all the ice is melted, the temperature of the drink rises back up again. And so that's because all the heat is going, that's in the drink, that's from the outside, that's coming into the drink, is basically going into melting the ice, not to changing the drink's temperature anymore. So latent heat is defined as being the amount of energy needed to change the phase of 1 gram of a substance. And our equation for this is Q equals MHL. And so similarly is that Q is energy or heat. I'm just going to go ahead and call it heat right here. And the unit of Q is just the same as it was before. It's in calories. Abbreviation for calories is CAL. And so that's Q. M is same as it was before. It's just mass. And it's mass. And so mass is the same as it was previously. Is going to be measured in grams. And then our last guy, our HL right here, this is called the latent heat, or the latent heat constant. So we're just going to talk about it down here. The latent heat required, so it has one of two forms. Is that basically there are two phase transitions that will happen that we're going to talk about here in chemistry. Those are from solid to a liquid or liquid to a solid, so melting or freezing, and from a liquid to a gas or from a gas to a liquid, vaporization or condensation. Now, if it's the first one, if it's one where we're changing from a solid to a liquid or vice versa, this is called the heat of fusion. And usually instead of writing HL, like see it's an L right here, it's instead is written as HF because it's the heat of fusion for F. So that's fusion, freezing, think those two together. That's what that one's going to cover. Now, if instead of melting or freezing, we're vaporizing something, the amount of heat required to change from a liquid to a gas is called the heat of vaporization. And instead of being HL, it's going to be HV is what we use here. For water, the heat of fusion is 79.7 calories per gram. The heat of vaporization is 539 calories per gram. So if you look at these, you can see it takes a whole lot more energy to vaporize water than it does to melt it. If I have a gram of ice, and it only takes 79.7 calories to be able to melt that ice. If I have a gram of water, it takes 539 calories to be able to vaporize that water completely into steam. And so this is what latent heat is right there. Let's move on a little bit and see a little bit about what this would look like. So right now, here's what we have. This is called a heating curve. Is that you should have either already by this point or should be soon basically generating one of these as one of your colored sheets. But basically what this shows is as you heat water, what happens to its temperature as you add heat. And so going through this on the x-axis down here, we have heat that goes this way. You can sort of see our heat right down there. On the y-axis, we have temperature, which goes up. And so temperature goes on the y-axis, heat on the x-axis. So basically we are adding heat going across here. Now if you take a look, we start off way down around this region right here. So we have down here solid ice. And so solid ice, because it's below the freezing point, which is 0 degrees, and so solid ice. As we add heat, slowly what happens? The temperature rises. It rises until it gets all the way up to 0 degrees. When it gets to 0 degrees, that ice is going to start melting. And so that ice starts melting, and when it melts, all of the energy goes just into melting the ice, not into raising the temperature. And so as a result, we have a flat line that runs across here. And so that's basically that first phase transition. This is where latent heat will apply. As soon as all the ice is melted, it's all liquid water now that we get to this point right here. Then we add heat, and what does the heat cause the temperature to do? Temperature rises. And that temperature will keep rising until it gets up to the boiling point of water, 100 degrees Celsius. And at that point, any new energy that's added is only going to go into vaporizing that water, into boiling it off. And so as a result, this whole section right here, latent heat is going to apply. It's going to be the heat of vaporization. And so that's why we can sort of see an HV right up here. And so all the energy goes in to vaporizing that water. So at this point right here, it's all liquid water. At this point right here, it's all vapor, water vapor. Once all the water's been vaporized, as we add heat, that's just going to cause the temperature of that steam to keep on going up, and that'll just go up indefinitely. There are a couple other things that are sort of on here. I don't know if you can read them very well, but what we sort of got here is you can see we start off with ice down here, sort of solid water. We start off with liquid water. We have liquid water after we melt it here. Then we have steam that's up here. Is that you can sort of see at the bottom, it talks about how we start off with solids down here. This part right here is a mixture between liquids and I did it again. It's a mixture between liquids and solid. Then we have a liquid phase that goes down here, which is on the section that's right up here. And then we have a mixture between liquids and gases, water and steam right up here. And then we have the gas phase, which is the very end. And so this table right here, this chart, will actually give you a pretty good idea if once you have your colored sheet set up with it, of what's going to happen once we start going ahead and doing these calculations on this. Because what you can do is if you're given a problem where you're told you have water at 25 degrees Celsius and you're going to add, say, 100 calories to that, what's the final temperature? Well, first thing you do is you'd say, okay, it's 25 degrees Celsius. Where is that? 25 degrees Celsius is right about in here. And so if it's right here, I can sort of ... I know I'm going to be on this section of the graph right in here. It's going to be this section here. Now, this section right here is liquid water. And since it's liquid water, we can say a couple things. One is we know the temperature's changing. If the temperature's changing, then that means we're going to have to use specific heat. Specific heat is Q equals Cm delta T. So that's our first part. What about our specific heat constant? Because we really didn't say anything about that one right there. What is this? Well, once again, it's liquid water. Since it's liquid water, we look for the specific heat of liquid water, and we find that that is equal to 1.0. And so I know my specific heat is, and if I'm given the number of calories I add, and I'm given the mass of my water, I can then find my change in temperature. And so from that, I can manage to solve the rest of the problem. And so that's how where this heating curve is going to end up being very, very helpful, is it's going to let us figure out some of these problems.